Hi everyone, today we're going to be doing 2011 number 2 for the AP Physics C mechanics problems. As stated before, the problem should be sort of next to you while you do it so that you can see the solution while looking at the problem, because I'm not going to show the problem, I'm just going to show the solution. And the link to the problem, if you want to see it, is in the description bar. So we're going to start. This is 2011 number 1. Okay, so in part A, they are asking for a free body diagram, basically, on the passenger compartment at point C. So when you're at point C, it's at a little curve in the ramp right here. This is point C. At point C, there's going to be two forces acting on it. So we can draw a dot. There's going to be mg, first of all, which is the weight of the compartment. And then there's going to be the normal force. And remember that the normal force is always perpendicular to the surface. So if you say this is the surface, then normal force is like this. Sorry, I was a little bit slanted. So that's the normal force. So it's going to be a little bit diagonal like that, and that's going to be labeled Fn, or the normal force. So that's it for part A. And then now for part B, they want, in terms of theta, the magnitudes of the forces drawn in part A, and determine an expression for the magnitude of the centripetal force acting in the compartment at a point C. So what I'm going to do is I'm basically going to draw the free body diagram again. So I'm going to say, okay, here is our compartment, and then here we have the normal force and force due to gravity, which is right here. Okay, and they want you to figure out how to use theta to determine the normal force. To determine the centripetal force. So our centripetal force in terms of theta is going to be basically the net force between the normal force and the mg, but we have to do it basically in the diagonal direction. So think about it this way. The centripetal force is going to be the force directed towards the center. So it's going to be the net force directed to the center, and it's going to be this normal force minus some force pointing this way. And we're going to later find out that that force is a component of the weight. So how do you figure that out? So what we're going to do, is we're going to draw basically a diagram to figure out how we can use theta to figure out the centripetal force. So if you look at the diagram that they give you, at point C, so point C is right here, there's that radius right here, and then there's theta right here. So we're going to draw a similar looking theta right here. So think about this as the normal force, theta is right here, theta is right here, and then we're going to draw a little, just sort of a perpendicular, just so we can see it the way it's here. So there's a theta here and a theta here. And then what we're going to do is we're going to find out, okay, how do we know what this component is? And the way we're going to figure that out is we're actually going to use triangles. So what we're going to do is we're going to draw a triangle right here. So this is a right triangle. And we're going to draw another triangle here. So this is also a right triangle. So these are both right triangles, and you have theta here. And you know that due to vertical angles, this angle and this angle are equal. So, based on congruent triangles, if this angle and this angle are equal, and this angle and this angle are equal, that means that this angle must equal this unknown angle. So we know that there is theta. So now we need to figure out this component with respect to theta, and we realize that because this is mg, this component is going to be mg sine theta. Because this is the hypotenuse, and we want basically the y component, or the component opposite theta. And sine is opposite over hypotenuse, so it's going to be mg sine theta. So now our net centripetal force is equal to Fc, so net centripetal force is equal to the normal force, so this force right here, minus mg sine theta. So that's our net centripetal force. All right. Now we're going on to part C. Part C is a conservation of energy problem, and they want you to figure out the expression for the velocity as the compartment reaches point D in terms of mr and other constants. So we're going to set up our initial conservation of energy equation, which is just initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. So KEI plus PEI is equal to KEF plus PEF. And we know that as it's falling from point A, there's no kinetic energy. So this goes to 0. And when it reaches point D, there is no potential energy. So this goes to 0. So now we have mgh, which is the equation for potential energy, is equal to 1/2 mvd squared. And our purpose is to solve for Vd. So now we have to find out what our h is, and the way they show it in the diagram is, so point A is here, and then it says it's like 3r over 4 here, and then it says there's some r over here. So basically, the way that we can solve for the total height is by saying this plus r. So 3r over 4 plus r, and that's going to be our total height from A to D. So we're going to plug that into our equation. So we're going to say mg 3r over 4 plus r is equal to 1/2 mvd squared. And then we're going to cancel out the m's because we don't need them anymore. So now we have g, and we're going to add these two up. So 3r over 4 plus r is 7r over 4 is equal to 1/2 vd squared. Multiply both sides by 2. So now we have 2g 7r over 4 is equal to vd squared. Cancel. So we get 7rg over 2 is equal to vd squared. And now we're going to take the square roots on both sides. Square root, and we get our final answer, which is vd is equal to the square root of 7rg over 2. And that's the answer to part C. Now for part D. Oops. Part D. Part D asks a sort of separate question. They say that if a force acts on the compartments between the points D and E, and it stops at point E, what is the coefficient of friction between the compartment and the track? So what we're going to do is we're going to first draw a quick diagram of what this is going to look like. So the block is here. Sorry, that's going to be supposed to be straight. The block is here. It's sliding from point D to E, and it has a normal force. It has mg, and it has the force of friction. We're going to call that little f, right? So we know that the force of friction, so F, is equal to mu times the normal force, which is equal to mu times mg. And we know that the work done by friction is the only work being done here. So the work done by friction, is equal to the change in kinetic energy. Because that's the only thing that's making it move right now. It's change in it's force of friction. That's the only thing that's causing work right now. So we're saying work due to the force of friction is equal to change in kinetic energy. And as it says in the problem, it stops at point E. It completely stops. So if work is equal to KE final minus KE initial, and KE final stops, that means this is 0. So we get work is equal to 0 minus 1/2 mvi squared. And we know that the force of friction is equal to force of friction times 3r, force of friction times 3r, because as it showed in the diagram of the problem, that's the distance between D and E. Distance between D and E is 3r. So remember that work is force times distance. So force, frictional force times distance is equal to mu mg. So we're just taking that from here and putting it here. Mu mg times 3r. So that is equal to, so mu mg 3r is equal to 1/2 m, and we're going to take the velocity that we got from the previous problem, the final velocity, and we're going to plug that in as our velocity, is equal to root 7 over 2 rg squared. And if we simplify that, that becomes mu mg 3r is equal to 1/2 m 7 over 2 rg. 7 over 2 here. And that's because the square root is squared, so it just becomes a normal quantity. So now we're going to cancel the m's. We're going to cancel the r's. And we're going to cancel the g's. And so what we get is 3 mu, so mu 3, is equal to 7 over 2 times 2, so 7 over 4. So mu is equal to 7/12. Alright, so that's part D. We were able to figure out what the coefficient of kinetic friction is. So now on to part E. E is probably the longest part of this problem. So we're going to take it step by step. Part E, I think, considers a case where there's no friction, but instead the compartment is brought to rest by a braking force negative kV. And then they give us the same constants, and they want us to solve a differential equation for Vt. So let's draw, as usual, a quick diagram of what this looks like. So we have our block, and there's no frictional force. Instead, there's a force, a braking force of negative kV. So if we were to draw, if we were to write a net force equation, it'd be net force in the x is equal to negative kV, or ma is equal to negative kV. And then we know that a is dv dt, or a acceleration is derivative of velocity, so m dv dt is equal to negative kV. So our differential for this problem is going to be dv over dt is equal to negative kV over m. I just moved the m down here and simplified, and this is our answer for part 1 of E. For part 2 of E, they want us to solve this differential for Vt. So we've done similar problems like this in the past, but we're going to go over the same process again. So we're going to say m dv dt is equal to negative kV, just like our differential did. And then we're going to make sure that dv and v are on the same side. So we're going to say, we're going to say dv over v is equal to negative k over m dt. All we did was I took the negative k, kept it there, moved the m over here, and then moved the v over here. Okay, so now we have this. Now we can just integrate both sides like we've done before, and we get that ln of v is equal to, because this is a constant, it's similar to just taking this out. So because this is a constant, you can just take it out and add a t, right? This is just integrating some it's like integrating 5. The integral of 5 is 5t. So that's what we're doing here. So ln v is equal to negative k over mt plus c. Don't forget that. And now we need to solve for c. So that's going to be the first thing that we do. So what we're going to say is that at 0, so at point D, when this is when, so v of 0 is equal to v at that point D, right? So we're starting from D and we're going to E. So our initial velocity or velocity at time 0 is equal to velocity at point D. So what we're going to say is that ln, and we're going to plug in vd, and time is equal to 0. So this whole thing is equal to 0. So ln vd is equal to c. So now we know what c is. So we can plug it back in, and we can say ln of v is equal to negative kt over m plus ln vd, which is our c. And then now what we're going to do is we're going to raise both sides to the e in order to solve for v. So raise both sides to the e. If you raise e to the ln, you simply just get that v. So v is equal to e to the negative kt over m e to the negative kt over m plus ln vd. So now we have this equation, and remember by the rule of exponents, if you have 5 to the 6 times 5 to the 3 is equal to 5 to the 6 plus 3, which is equal to 5 to the 9. So we're going to use the same sort of format here. Here we have e to something plus something, so we're just going to split it up. So it's like having 5 to the 6 plus 3, we have e to this plus this. So we're going to split it up like we did over here. So it's going to be e to the negative kt over m times e to the ln vd. And just like we had here, we had e to the ln, we realized that this just goes to vd. So now we have v is equal to e negative kt over m vd. Or v of t is equal to vd e to the negative kt over m. And that's how you get the velocity. Alright, so that's the second to the last part. And then the very last part, part 3, is asking you to sketch a graph of the magnitude of the acceleration as a function of time. So they give you a graph. Let me just draw that down here. Here's the graph. And time is on the bottom. And they want you to draw the acceleration. So first what we're going to do is, we know that the acceleration is the derivative of velocity. So a of t is equal to d over dt v of t, which is equal to d over dt, the expression we just found, so vd e to the negative kt over m. So we're going to differentiate this, and we get that a of t is equal to, take out the constant, vd, and then e to the negative kt over m, and then multiply by negative k over m. So what we know now is that negative k over m is multiplied by all of these things, and we know that vd is a constant. So what we're going to do is simply, we're going to take the magnitude of this, so the absolute value, because as it says in the graph, they want the magnitude of acceleration. And we're going to say it's equal to k vd over m e to the negative kt over m. So if you graph e to any negative, so e to the negative x, it looks something like this. I'm just going to do a quick sketch. It looks something like this. like this. So we're going to expect our graph to look something like that. And then what we're going to do is at t equals 0, so at the initial point, so when t is equal to 0, e is equal to 1, right? Because e to the 0 is 1. And so at t is equal to 0, the acceleration is equal to kvd over m. So our starting point is at kvd over m, and then it goes like this. And then that's it. That's the end of the problem. You've done all parts.